All right, ready to dive into some serious material science.
Always.
You sent us this research paper titled Corrosion Behavior of NaNB Eutectic Glassy Composition.
Sounds a little intimidating, I know.
Intense. But hey, that's why we're here, right?
Right, exactly. We're going to break it down.
We're going to break down this 2024 research article.
From the Journal of Materials Engineering and Performance. Quite a mouthful.
Yeah. So you can walk away feeling like, you're ready to go head-to-head with a material scientist.
Well, maybe not head-to-head, but you'll definitely have a better understanding of this amazing material.
And trust me, when you hear about this stuff, you won't believe we're talking about glass.
It's really remarkable.
This isn't your grandma's window pane. This special metal glass can withstand even the harshest chemicals.
It's true. The resistance to corrosion is something else.
So let's unpack this. How do they even make this NaNB alloy? What makes it so tough? And then the big question, where could this stuff be useful?
So many good questions. Let's start with how they make metallic glass, which I have to admit sounds like something straight out of a sci-fi movie.
Right.
Okay, picture this. Molten metal, like literally glowing hot metal, blasted onto a spinning wheel at insanely high speeds.
Okay, I'm picturing it. Keep going.
It cools down so fast, you see, that the atoms don't have time to arrange themselves neatly into a regular crystal structure.
So it's like freezing metal in midair before it can, decide how to arrange itself.
Precisely. And in this research, they actually used two different wheel speeds, 12 meters per second and 25.
Okay, so two different speeds. Does that mean they get two different types of metallic glass? What's the impact of changing that?
Or it's fascinating how that seemingly small change can actually lead to some pretty significant differences in the material's properties.
That's so cool. I'm already seeing how they're fine-tuning this stuff. But hold on. How do we know for sure that they actually made a metallic glass? I mean, it sounds cool, but...
Good point. They need proof. They use this technique called X-ray diffraction.
X-ray diffraction, XRD.
Yeah, exactly. And that essentially lets them peek into the internal structure of the material.
So kind of like an X-ray, but for the metal's internal structure. It's like looking at its bones.
Exactly. And what they saw was this diffuse peak in the XRD pattern, which is a telltale sign of that random atomic arrangement you find in glassy structures. So it confirmed they're dealing with the real deal, a true metallic glass.
All right, so we've got our metallic glass. What did they do? Just throw acid on it and see what happened?
Well, not exactly throw, but they did want to test its limits, right?
Of course. Got to see how tough it really is.
So they put this NaNB alloy to the test in 3 different, super harsh environments.
I'm guessing acid was one of them. What were the others? Give me the rundown.
You got it. Hydrochloric acid, or HCl for short.
Yeah.
Then they used sodium chloride, NaCl, which is essentially a super concentrated salt solution like you'd find in the ocean, but way more intense.
Okay, makes sense. And the last one?
And lastly, they used sodium hydroxide, NaOH, to create a highly alkaline environment.
Okay, so we've got acidic, salty, and basic. Quite the lineup of challenging conditions. But how do you actually measure how well a material holds up? I mean, is it just like, yep, it corroded, or nope, it didn't?
It's a little more nuanced than that. Think of it like a detective story. Scientists have a couple of tools at their disposal. One called EIS, which stands for Electrochemical Impedance Spectroscopy, and cyclic polarization.
EIS, that sounds like a mouthful. Can you break it down for us?
Well, it's a bit technical, but essentially EIS is like giving the metal a lie detector test. You see, it measures how the metal reacts to electrical signals in each of those environments.
A lie detector test. So are we trying to trick it into confessing that it's corroding?
Kind of. It's about revealing how well the metal resists the urge to corrode. It's looking for weaknesses, any cracks in its defenses.
Okay, I'm starting to get it. What about cyclic polarization? What does that tell us?
Cyclic polarization takes things a step further. It's like putting the metal through boot camp, exposing it to increasingly harsh conditions, then backing off a bit and seeing how well it recovers. It's about finding the metal's breaking point, so to speak.
Wow, they really put this stuff through the ringer. I'm on the edge of my seat. So, spill the beans. What did the results show? Was our alloy able to stand up to all that?
The results were pretty impressive, especially in those acidic and neutral environments, pH 0 and 7. The alloy was practically immune to pitting.
Wait, so even in strong acid, this metal didn't corrode? I'm intrigued. What exactly is pitting, anyway? I'm not a material scientist, so...
Right, of course. So pitting is a sneaky kind of corrosion. It's where tiny holes or pits start to form on the surface of the metal, like it's being attacked from within.
Ah, so it's not just surface rust. It's more insidious, like little holes eating away at the metal's strength.
Precisely. And it can significantly weaken the metal over time.
Got it. So this 9Nb alloy managed to completely avoid this pitting corrosion.
Exactly. It showed incredible resistance in those environments. And get this, it even displayed signs of self-healing.
Hold on. Self-healing? Okay, this is starting to sound like something out of a superhero movie.
Yeah.
How is that even possible?
It is remarkable. Even when the surface of the alloy was damaged, it could actually regenerate its protective layer, almost like it had a superpower, right?
That's wild.
Oh.
Okay, I need to know more. What's the secret behind this self-healing ability?
Well, the key player here is niobium oxide. It's this compound that forms on the surface and plays a crucial role in forming that protective barrier and repairing any damage that occurs.
So the niobium oxide is like the metal's own little repair crew, constantly patching up any vulnerabilities. And I'm guessing this is why this alloy is so much tougher than traditional metals.
Exactly. Most traditional metals would corrode much more easily in these kinds of harsh environments. But this 9B alloy, with its unique composition and structure, it just shrugs them off. You know, it's amazing when you think about it, the amount of research and effort that goes into understanding these materials at such a, fundamental level.
It really is mind-boggling. Peeling back the layers of an onion, right? Every test they do reveals another little detail, another insight into how this alloy behaves.
That's a great analogy because in this case, they didn't just stop at proving that it was tough. They really want to dig into the why. Why is it so resistant?
The why behind the wow, right? And that's where those high-tech tools come in, like the XPS you mentioned earlier.
Yeah.
It's not enough to just know what's there. We need to understand how it got there, what it all means.
Exactly. By analyzing the specific types of oxides on the surface and their ratios, they can start to piece together the mechanism, like how those oxides are actually forming and what role they play in the alloy's overall behavior.
Okay, and this self-healing ability, this is what's really blowing my mind.
Mm-hmm.
Is this something we see in other materials? Or is this alloy truly unique?
That's what makes this research so exciting. I mean, sure, some materials might exhibit limited self-repair capabilities.
Right.
But this alloy's ability to regenerate that protective layer in such aggressive environments, that's really remarkable.
Okay, so paint me a picture. How does this self-healing process actually work?
All right, so imagine this. When the alloy is exposed to those corrosive environments, the niobium oxide, right, it forms this sort of protective barrier on the surface.
Okay, a barrier. Got it.
Almost like a microscopic suit of armor protecting the metal underneath.
So that's the first line of defense against those corrosive attacks.
Excellent.
But what happens when that barrier is, breached? That's when the self-healing kicks in, right?
Precisely. If that protective oxide layer gets damaged, the niobium oxide can actually move to those damaged areas and repair them.
No way. So it's like it's got its own little repair crew on standby,
Mm-hmm.
constantly patching things up.
Exactly. Instead of just degrading over time like most materials would, this alloy can actually bounce back, maintain its integrity even under intense stress.
Man, that's amazing. The implications of that are huge. I mean, think about all the applications where you need something that's going to last, something that can hold up to a lot of wear and tear.
Huge implications, exactly. Things that are constantly exposed to, like corrosive fluids, extreme temperatures, you name it.
Pipelines, bridges, implants, the list goes on.
Yeah.
If they could repair themselves, it would save so much time, money, hassle. Not to mention, safety concerns as well.
Absolutely. Safety is a huge factor.
Okay, so I'm seeing the potential here. It's huge, but, nothing's perfect, right? There have to be some challenges. I mean, working with these new materials, especially metallic glasses, it can't be easy.
You're right. There are always challenges when you're dealing with cutting-edge technology. And with metallic glasses, one of the big ones is scalability.
Scalability.
Yeah.
So we can't just, start churning this stuff out tomorrow and replace everything.
Not quite yet. Right now, they're making these alloys in, relatively small batches using these specialized techniques.
Like melt spinning, right?
Exactly, melt spinning. And it's not easy to scale that up to, mass production levels.
Right. So there's a lot of research and development that still needs to happen.
Exactly. But as research progresses, as technology advances, we might find ways to produce these alloys on a larger scale and, importantly, at a lower cost.
Okay, fingers crossed, because if we can mass produce this material, the possibilities are just I mean, I can't even imagine.
The possibilities are endless. It would be a game changer.
Okay, so scalability is one challenge. Are there any other hurdles scientists are facing with metallic glasses?
Another big one is understanding the long-term behavior of these alloys. I mean, we know they're incredibly resistant to corrosion, right?
Right, in the lab.
Yeah, in a controlled setting. But what happens after, like, years, decades?
Out in the real world.
Exactly. More research is needed to really understand their long-term durability.
So it's kind of a waiting game, right, to see how they hold up over time.
It is a bit of a waiting game. But that's part of what makes materials science so exciting, isn't it?
Always something new to discover. It's a constantly evolving field.
Exactly. Now, remember how we were talking about the 2 different wheel speeds they use to make this alloy?
Oh, yeah. And how that, like, tiny little tweak in the manufacturing process could lead to such a big difference in corrosion resistance. But I'm still a bit fuzzy on the why. Like, what's the connection there?
It all comes down to understanding the link between the material structure at, like, the atomic level and its overall properties.
Okay, I'm all ears. Break it down for me.
So when you change the wheel speed during melt spinning, you're essentially changing how quickly the molten metal cools down. That cooling rate has a huge impact on how the atoms arrange themselves as the metal solidifies.
Okay, so faster wheel speed means faster cooling.
Right. And that faster cooling leads to a more amorphous structure, a more glassy structure, basically.
Got it. Less time for the atoms to settle into their little, crystal patterns.
Precisely. And because of that rapid cooling, you end up with fewer defects in the material.
Defects, like cracks and stuff.
Exactly. Tiny cracks, voids, those kinds of things. And even though they're super tiny, they can act as weak points, like places where corrosion can start to take hold.
Ah, so it's like having a perfectly smooth surface.
Right.
Right, at a microscopic level.
Yeah.
If there are no nicks or scratches, there's nowhere for the corrosion to get a foothold.
Exactly. It's like a chain, If you have one weak link, it doesn't matter how strong the other links are, that one weak link will be the point of failure. But if you have a smooth, defect-free chain, it's much, much stronger.
That makes perfect sense. So
Yeah.
the faster wheel speed, by creating that smoother surface, that more uniform structure, it's basically giving the alloy a super boost in corrosion resistance.
Exactly. And it really highlights how even those tiny, seemingly insignificant changes in the manufacturing process can have a dramatic impact on the final properties of the material.
It's like the devil's in the details, right?
Yeah.
And it makes you appreciate the level of precision and control that goes into material science. It's not just about throwing stuff together and seeing what happens.
What a very precise science. A delicate balance.
So fascinating. All right, so we've covered a lot about how this alloy is made, how it's tested, and how its structure influences its properties. But what about the researchers themselves? Did they have any specific thoughts on potential applications for this NaOH alloy? What were they most excited about?
Well, they were particularly enthusiastic about applications in what they called harsh environments. They really emphasized the need for further research in those areas.
Okay, harsh environments. Give me some examples. What are we talking about here?
Things like pipelines, deep sea equipment, maybe even components for spacecraft, places where the materials are really put to the test.
Okay, yeah, those are some pretty extreme conditions.
Yeah.
So they're not just talking about, like, making a better frying pan, right? They're thinking about things that can really make a difference in challenging fields.
Exactly. It's not just theoretical. They're looking for real-world solutions to real-world problems.
That's what I love about material science. It's that bridge between the world of, like, fundamental scientific discovery and practical applications. It's so cool. But before we get too carried away, let's actually talk about some of those applications in more detail. Where do you think this super tough, self-healing alloy could make the biggest impact?
One area that really jumps out at me is bioimplants. Imagine like hip replacements or bone plates that are not only strong and durable, but also resistant to the corrosive environment of the human body.
Okay, I'm listening. That's something that, like, hits close to home for a lot of people.
Right. And because this alloy is so biocompatible,
Biocompatible.
meaning it doesn't trigger a negative reaction from the body.
Okay, good.
So it's an ideal candidate for implants, hip replacements, bone plates, you name it.
So we're talking about, like, longer lasting implants, fewer surgeries, less pain and discomfort for patients. I mean, that's a huge quality of life improvement.
Absolutely. And that's just one example. This alloy has the potential to like revolutionize so many different fields.
Okay, what else? I'm ready for more.
Another area that's really interesting is harsh industrial environments, like what you find in the oil and gas industry, for instance.
Okay, I'm picturing, like, pipelines, drilling equipment, all that stuff that's constantly exposed to corrosive chemicals, high temperatures, extreme pressures.
You got it. Those are the kinds of places where this alloy could really make a difference. Traditional materials often struggle to withstand those conditions, which can lead to, costly repairs, downtime, even safety hazards.
Big problems.
Big problems. But with this NaNB alloy, with its toughness and that incredible self-healing ability, we could be talking about much more durable, reliable equipment.
Increased safety, increased efficiency. It's a win-win. Okay, this is all really impressive. But let me throw a curveball at you. What about something a little more out of this world? Any potential for this alloy in space?
Now you're thinking big. And yeah, you're right. This alloy's properties make it a really good candidate for aerospace applications.
I'm talking spacecraft, satellites, maybe even like habitats on other planets. Those environments are incredibly demanding. You need materials that can handle extreme temperatures, radiation, micrometeoroids, the works.
Exactly. The harsh conditions of space really push materials to their limits, and this alloy seems like it could be a real game changer in that regard.
Plus, it's lightweight, right? Which is crucial for anything going into space.
Oh, absolutely. Weight is always a major consideration. So any material that can offer that combination of strength, durability, and lightweight is a huge advantage in aerospace applications.
It's like we could be on the verge of a new era of space exploration thanks to this alloy. It's so exciting to think about. But before we get too carried away, did the researchers in this paper specifically mention any particular applications they were most interested in? Like, did they hint at what direction they thought this research should go in next?
Well, they did emphasize the need for further research to really nail down those specific applications, especially in those harsh environments we talked about. But they seem to be leaving it open, like an open invitation for other researchers to take what they've learned and run with it.
It's a collaborative effort. That's how science progresses.
Exactly. And it's exciting to see how research like this can spark so many new ideas and possibilities.
Well, I don't know about you, but my brain is officially buzzing with all the potential of this alloy. Feels like we've only just scratched the surface.
We've just scratched the surface. There's so much more to explore.
All right, well, I can't wait to hear what other surprises you have in store for us in the final part of our deep dive. What can our listeners expect next?
In part 3, we'll dive into some of the other remarkable properties of metallic glasses, talk about the challenges that researchers are facing, and maybe even speculate a bit on what the future holds for these incredible materials.
Okay, we're back for the final part of our deep dive into NaNB metallic glass. We've talked strength, we've talked corrosion resistance, self-healing. Is there anything else this wonder material can do?
Oh, we've only just begun to explore the amazing world of metallic glasses. There are a few more surprises I think you'll find pretty fascinating.
All right, lay it on me. What else can these metallic glasses do?
One thing that I always find interesting is their elasticity.
Elasticity?
Yep.
Like stretchy? I thought we were talking about metal.
I know, right? It seems counterintuitive. But metallic glasses can be surprisingly springy. Like they can bend and flex under stress, but then they spring right back to their original shape.
No way. Most metals I know are either strong or flexible, but not both. How is that even possible?
It goes back to that lack of a regular crystal structure. Remember how we talked about that?
Yeah, the whole amorphous thing.
Right. So without those rigid crystal boundaries you find in traditional metals, the atoms in a metallic glass have more freedom to move around.
So they can kind of roll with the punches, so to say.
Exactly. They can rearrange themselves under stress and then bounce right back instead of just cracking like a brittle material would.
Okay, that's pretty impressive. Where could this combination of strength and elasticity be useful?
Well, think about applications where you need a material that can withstand impact and repeated bending.
Okay.
Things like springs, maybe flexible electronics, even sporting goods.
Interesting. So we've got strength, we've got corrosion resistance, self-healing, elasticity, anything else. What other amazing properties are hiding in these metallic glasses?
Well, their conductivity is another important one, both electrical and thermal conductivity.
Okay, so now we're talking about the ability to conduct electricity and heat. Are they good conductors, these metallic glasses?
The answer is, well, it depends. It can vary quite a bit depending on the specific chemical composition and how the material is processed.
So some are good conductors, some are not.
Exactly. It's a spectrum.
What are the implications of that?
Well, some metallic glasses have incredibly low electrical resistance, like really, really low, which makes them very attractive for things like advanced electronics.
Wow. So they could be used to make better, faster, more efficient electronics.
They could, especially for high-performance transistors, wiring, maybe even superconducting materials. There's a lot of potential there.
Okay, but you said potential. So I'm guessing there are still some challenges. What's holding us back from fully realizing the potential of these amazing materials?
One of the biggest hurdles is controlling the properties of the material during the manufacturing process.
What do you mean?
Even the slightest variations, like temperature changes during cooling or impurities in the metal, even tiny amounts can have a big impact on the final product.
So it's a pretty delicate process.
Very delicate. It requires really precise control over every step of the way.
Sounds like these material scientists have their work cut out for them.
They do, but it's a very exciting field to be in right now.
I can imagine. Well, this has been an absolutely mind-blowing deep dive. I feel like I've learned so much about metallic glasses, and honestly, I'm just blown away by their potential. Before we wrap things up, can we just recap some of the key takeaways?
Sure. So first of all, I think we've clearly established that metallic glasses are a unique class of materials with a pretty remarkable set of properties.
Right. Strength, elasticity, that incredible self-healing ability, the conductivity, and all of it stems from that unique amorphous atomic structure.
Exactly. They break the mold when it comes to traditional crystalline metals.
And specifically this NaNb alloy that we've been talking about, it's just, wow.
Super tough, especially resistant to corrosion, even in the harshest environments.
I mean, from bioimplants to aerospace components, it seems like the sky's the limit in terms of potential applications.
The sky's the limit. But of course, there's still a lot of work to be done, especially when it comes to, scaling up production and really fine-tuning those properties.
Right, those are the challenges for the future.
The challenges, but also the opportunities.
It's almost like we're witnessing a new era in materials science.
It's a very exciting time to be following this field.
Well, I want to thank you for taking us on this incredible deep dive into the world of metallic glasses. It's been a real pleasure learning from you.
It's been my pleasure as well. I'm always happy to share my passion for material science.
And to our listeners, thanks for joining us on this journey. If you're as fascinated by metallic glasses as we are, well, we encourage you to do some exploring on your own. There's a whole world of amazing science out there just waiting to be discovered.
Keep learning, keep exploring.
And keep sending us those research papers. We're always on the lookout for new and exciting topics to dive into. Until next time.